Hello, everyone. My name is Rishita, and on behalf of our team, which includes Gaurav and me, I'm going to give a theory approach on Lempel Ziv Welch compression. So let's start with the introduction. So today we are diving into compression algorithms. Our world is flooded with data, and we need fast and efficient ways to handle it. Whether we are saving old photos, archiving lots of surveillance data, or streaming content on our favorite platform, the data needs to be smaller and faster to use. For YouTube, saving few bytes in transit can result in significant reduction of server cost as well as an experience for user that is buffering free. LZW algorithm. It was created by Abraham Lempel, Jacob Siv, and Terry Welch in 1984 as an improved implementation of LZ78 algorithm. It is used as compressed file compression utility of Unix and a popular GIF image format. What are the key points of compression? It should be smaller or equal to the size of the original string. It should be reversible irrespective of the context. And any information that's saved other than the data itself defeats or reduces the efficiency of the algorithm. Therefore, the compressed string should be formulated in such a manner that it can decode itself. Every day, we are creating and communicating billions of terabytes of digital data. If it were written on a paper, it would represent millions of libraries worth of data created every day. So, we are always looking for ways to squeeze more data into less space. One approach is to design smaller and smaller memory media, but no matter the medium, there is a second mathematical tool we can use, such as we take advantage of patterns in our data. We can use them to compress the size of our files as much as possible. Just the challenge is to do the compression in such a way that enables reverse the process and uncompress the data without losing any information. This is known as lossless compression. For this, people devised code books which map a specific set of common phrases into short letter sequences or codes using a lookup table. For examples, Simon's codebook contains common phrases used as such as I have an anchor on board which can be expressed in a code AAC, while the cotton merchant code maps the phrase our prices are below surrounding markets to the word class. So if two people share a copy of codebook, they can communicate long phrases in such a word or two without losing any information. But the problem was this codebook approach do not contain every possible sentence you might want to send. Just the most common sentence is for a specific kind of conversation. And if the type of conversation changed, the codebook would no longer be in use. This problem leads us to a more general approach where a single codebook is used no matter the type of conversations. For example, one way could do would be the create a codebook based on the words of a given language. The idea is to map common word in any language to shorter sequences and to map the less common words to longer sequences. This approach was nice because all possible conversations in a language can be compressed using a single codebook. Well, this codebook works in general, no matter the conversation type. The conversation achieved with this strategy is not as good as the codebooks designed for a specific kind of conversation. So we are left with a key problem. How can we achieve the high compression of conversation using a specific codebooks while maintaining the simplicity? To this problem was presented in a paper published in 1978 by Jacob Ziv and Abraham Lempel, leading to known as Lempel-Ziv compression. In the paper, the book specific to every message we send that is we could take each message we want to send and scan it looking for a repetition and design the ideal code book for the message which maps the most common sequence in the message to shorter sequence. The sender can then use the codebook to compress the message But of course, the receiver won't know to interpret the data unless you first send the codebook as well. The goal was therefore to design this codebook such that the codebook plus the compressed message is shorter than the original message. This is critical to make this method work, and then the sender can send the compressed message with the codebook attached. The receiver then uses the codebook to uncompress the message to get back the original. The Lemper-Ziv-Welch compression method builds a codebook dynamically as it scans the message. When encountering a new sequence, it adds it to the codebook and sends the code excluding the last character. This allows for compression on the fly without needing a predefined codebook. The receiver constructs the same codebook based on the received codes, enabling decompression without requiring the sender to transmit the codebook separately. This approach efficiently compresses data and is widely used in various applications, including data compression, pattern matching, and machine learning. Initialization. Both the sender and receiver start the empty codebook scanning the message. Sender scan the message AABA, BBA, BBAA, letter by letter. It starts the process. The code the first entry sender encounters A, again formatting the sequence AA. Since AA is already in the codebook, it continues. Next, it encounters B, forming the sequence AB. AB is new, so it's at the codebook, and the code for A1 is sent sender continues, forming BA and BB, which are new, so they are added to the codebook. And the code for B, which is 2, and AB, which is 3, are sent respectively. It proceeds similarly for BA, BB, and AABA. Each time adding new sequence to the codebook and sending their codes. The sender codes the sequence of code 11232547. Receiver reconstruct the codebook in the same way as the sender. It decodes the sequence of code back to the original message, which is AABA, BBA, The original message is successfully compressed and decompressed using the LZW algorithm, with no need to transmit the codebook separately. Both sender and receiver dynamically build the same codebook during the process. Now we